going to start again with the last introductory lecture of today, where we're going to talk about entirely different calibration altogether. Richard Wilkinson from the University of Nottingham is going to talk about calibration of computer models. Please.
Thank you, Thordis. So yeah, confusingly, calibration here means something somewhat different to the sense in which it was meant in Joanna's and Vladimir's talk this morning. So there they were using it as a property of a forecast. It was calibrated if it had certain statistical properties. In the context of computer models, I'll explain what I mean by that in a minute, it's more a process that we go through to make the computer model prediction look somewhat like reality in some way. So what do I mean by calibration? What does this community mean by calibration? Well, it's got various names, so variously called parameter estimation, fitting, tuning, an inverse problem, system identification, and so on, and probably other things as well. But the basic idea is that we've got some sort of model or simulator, I'm referred to this, handed to us by a scientist, an engineer, an expert in some domain, and they probably spent some time investing in this model. So probably the result of various PhD students and postdocs work over a large amount of time, but it's a model someone's put a great deal of thought into. And in this model, we're going to have some parameters x that we're going to want to estimate in some way, some parameters that are unknown, and we want to learn them from data in some way. I'm going to have another input, u, which I call a control input here, but it doesn't control anything necessarily. It's just another input that affects the simulator in some way that we don't want to estimate, that we're just going to vary. Okay, and I'll give an example in a second. So, given a model, f, we're going to then be given some data, some observations on a real process, a real physical thing. They're going to be collected under some collection of experimental conditions that might relate to this control variable u in some way. Okay. And maybe they'll give us a hint about how the simulator relates to the data. And what we're going to want to try and do from y is estimate the best input parameter, which I'm going to call x star here. Okay. So we're going to imagine there's a single best input, x star, that in some way makes the simulator look like the data. And what we want to try and do, well, calibration then, I guess, is adjusting our x star until the simulator prediction looks like the data y. So the calibration of that process, that inverse problem of finding x from data y. And largely here, I'm going to be talking in the context of deterministic simulators. So each time you run it, it's going to be the same. Okay. We can also think in terms of stochastic models. Okay. So stochastic models are often, well, you can think of them as deterministic models where one of the inputs, which you might not think about explicitly, is just a collection of uniform random variables. Okay. So we're going to think about stochastic models that arise in this way as well. But generally, we're going to be in this kind of deterministic setting. Okay, so in pictorial form, f here, I've got y on the axis here and x on this axis. Okay, so f is a relationship between x and y. Someone's going to come along and tell us y, the data. And calibration then is the process of drawing this line across here and reading down what x star is, what the best input is given that y. And it's fine if we have just a single y here, we just get a confident, precise answer for x star. But someone might come along with an interval for y. In which case, if they do that, we might get an interval for the best input. Okay? So it could be over here or it could be over here. Both are consistent with y lying in this interval. Now, of course, mostly we think in a probabilistic way. The dominant paradigm, like mentioned before, for UQ is a kind of Bayesian setting. So we often think of a distribution for y. And if we have a distribution for y, that's going to induce, or we're going to hope to try and find a distribution for x, that when we push it forwards through the simulator, gives us back this distribution here. So calibration is the process of finding a distribution here for x, that when we push it through the simulator, it gives us the distribution we believe we have for the data y. Okay, and I thought it'd be useful just to give a motivating example from college-active digital twins. It's where most of my work is now. So if you've not heard of digital twins before, it's basically a jargon relabeling in the literature in the past 5-10 years for computer models with uncertainty. But the idea is, instead of modelling a generic phenomenon, whatever it is you're modelling a specific physical thing. So in cardiac digital twins, we're not just modelling hearts. We're going to try and create a model, a digital twin of a particular person's heart. Okay? So a patient's heart, we're going to collect data from that patient, and we're going to try and create a model that looks like that patient. Okay? So the heart is an organ we understand relatively well compared to most organs. It's just an electromechanical pump. You think of it as a bag of muscle. Blood flows into it, an electrical wave starts somewhere on that bag of muscle, and that wave spreads over, propagates over the surface of the heart, and as it does so, the muscle contracts. It contracts, it pumps blood. Okay? So this is just what happens at a single cell, a cardiac myocyte. If we see some stimulus, the cell depolarizes, it's called, the muscle contracts, and it takes some time to recover. Fine, okay? So we can build this into models of chambers in the heart. So the heart has 4 chambers, a left and right atrium and a left and right ventricle. Blood flows into the atrium, gets pushed into the ventricles. The ventricles are the big muscular bit that pushes it around the body. And lots of problems initiate in the left atrium. Okay? So this is a simulation of what electrical activation should look like. So we've got an electrical stimulus starting there, and that starts a wave that propagates over the surface of the heart. There's no mechanics here, this is just electrophysiology. We've got a wave spreading, and then we see the recovery of the wave in the blue and green and red afterwards. Okay. That's what it should look like. So atrial fibrillation is when this goes wrong in some way. You might get uncoordinated electrical waves, and when they become uncoordinated, the heart doesn't beat properly. Okay. So this is an example of electrical fibrillation, atrial fibrillation. We've got these waves that just keep going round and round and round in an uncoordinated manner. And every time the wave front, the blue, gets somewhere, the heart contracts, that bit of it contracts, but because the wave's all over the place, it doesn't contract in a way that causes the heart to pump efficiently. Now, I think any heart is capable of this kind of pattern, but most people's hearts, and healthy hearts, these patterns die out. They don't sustain. Okay? Whereas in some patients who have arrhythmias, they keep going. So these people who have atrial arrhythmias, atrial fibrillation, they get stuck in that kind of mode where those patterns just keep going round and round and round. So it affects about 500,000 people in the UK. And one of the main treatments is catheter ablation. Okay. So what they do, they send electrodes up onto the surface of the heart, and they burn the surface of the heart. And those burn marks don't conduct electricity. Okay. And the idea is if you put the burn marks in the right place, it will stop those waves going round and round and round. But unfortunately, in about 40% of cases, that's unsuccessful, and the patient then needs to go and have another ablation therapy. Okay? And each of these therapies has a risk of stroke, death, something terrible happening to you while you undergo a procedure. So, how do we get back to this? So, spreading waves is something we understand very well. We can model, scientists can model spreading of electrical waves very cleanly. So, the hope here is to build models that, given some atrial geometry, so given one of these shapes here, okay? This is from an MRI scan of a particular patient. So given the shape of their heart, can we simulate the voltage at different locations in that heart through time? So there's various different sets of models. They're all PDEs, they're all these, diffusion type models. And these models all have different parameters. And these parameters are specific to individual patients. Because in disease patients, these parameters have probably been modified in some way in that patient. The geometry is specific as well. So what we're going to do is try and calibrate this model, adjust these parameters so that we get voltage maps that look like what we observe. Okay, and these models have a stimulus. And so what we typically do here is, the cardiologists do here, that they'll provide a stimulus somewhere in the heart, and then at a number of locations on the heart, the circles here, if you can see them, they have an electrode they wave around, and they measure how long it takes from the wave being set off at time 0 to time to reach these bits. So we don't observe all the colours here. The colours are our interpolation on this manifold. But what we get is the time the wave gets here. And what we want to try and do then, on the basis of this, we want to try and estimate something about the parameters. So I've written it in a Bayesian way here. We're trying to estimate what we now believe about the best input parameters, my x star here. So they were parameters in this PDE. Okay? What we believe about those parameters, given some data, where we're going to assume the data comes from something like the model run at those inputs. And when they do this in the clinic, the surgeon provides a stimulus so you know when the model's paced, when the heart's paced. And on the basis of that, we then want to make a prediction about what will happen if we take some action A. So if we do some treatment. So we want to predict whether, after we've done this action A, this ablation, will atrial fibrillation still be sustained? So in other words, we want to, the model gives us this bit. It tells us, we can simulate, that was this simulation. We can simulate atrial fibrillation, and we can see if it's sustained in a given heart or not. But we can only do that if we know X star. So if we integrate out the uncertainty in X star, we get a prediction here. Okay. So this is kind of an impossible challenge in some sense here. There's no hope of achieving this, at least in the full generality. These parameters, X, at least in the model I wrote down, were spatially varying. Okay? And we've got really sparse, noisy data. So we're not going to be able to estimate it without making strong assumptions about how X varies. The model here, F, is really expensive to run. It takes about an hour on a HPC to run once. Okay? So we're not going to be able to do tons of simulations. We don't really know the geometry of someone's heart, and so on. And to be useful then as a tool, not only do we need to solve this impossible problem, we're going to be able to solve it fast. In that typically the surgeon collects the data and then wants to do the procedure, the ablation procedure, 10 minutes later. So you maybe got 10 minutes to solve this calibration problem to be useful. It's going to be cheap as well. To be useful in the NHS, at the moment we spend about £1,000 doing simulations for one patient. In order to do this, we need to get that cost down. And it needs to be scalable. At the moment, it takes a postdoc 3 months each time we need to do this for a new patient. So it needs to be something we can scale across the population. It needs to be accurate as well, of course, and robust and all the other things. Okay. So this is kind of the challenge that I think we face in calibration, in using calibration in real-world examples where we've got complex models. We know we're going to have to make compromises somewhere and do some things that are not so attractive to us as careful mathematicians. But if we want, the answer is, can we do unattractive things and still get useful answers at the end? Is there a way of making any progress and saying anything about these things? Okay. So what I'm going to do this talk then, back to kind of generalities rather than specifics, example, talk through the kind of the key decisions we have when we're calibrating the model. Okay, so this is Chris Lanyon and I wrote a review on this last year, and we kind of broke down the challenge in this way, so I'll just go through that way of thinking here. So first of all, I think it's useful to think about what is it we care about before we jump in with the calibration, because what we care about is going to affect how much time we need to spend on each decision. Then we need a calibration framework. How are we going to characterize uncertainty? How are we going to think about uncertainty? How are we going to define what a good model is? The trickiest part is often this observation error, which is specifying how the simulator relates to the data in some way. And then finally, the part most people probably are most familiar with is computation. How do we compute these things? What options do we have? Okay. So just before we jump into that, just one preliminary on identifiability here. One of the things we often do before we start with any problem is try and cut down on kind of gross non-identifiabilities. So we might say a model, parameter X, is structurally identifiable if when we run it at 2 different inputs, we get 2 different simulations. Okay. And when we have these big complex models with lots of parameters that the scientists don't really fully understand, we often get non-identifiabilities. and their parameters we can't hope to estimate, no matter how good our parameters or how much data we have, you just structurally cannot learn them. People often think about practical identifiability as well. So for example, they might compute this Fisher information matrix, and as long as that's full rank, or if it's the diagonals of the inverse of it aren't too big, you might think you could learn about the parameters. Okay. Now that's kind of an abstract definition of identifiability. Unfortunately, in most kind of complex models, we can't answer these questions. We can't evaluate these things, at least not globally. So what we often do instead is use sensitivity, some sort of sensitivity metric, as a proxy for identifiability. So, for example, in global sensitivity analysis, we often compute what are called these Sobol indices, and they think about how the function varies through space as we vary one input at a time. So if we just focus on this one, this says if we just think about how the function varies with one of the inputs and we average over all the other inputs, and then we think about how variable that response surface is here. And we can estimate these things fairly straightforwardly. There's good packages for doing it. And we then kind of make these indefensible kind of statements at the end, that, like, if these indices are 0, so the input's not sensitive, it strongly suggests that X isn't identifiable. Doesn't imply it, but it strongly suggests it. And conversely, if these are non-zero, we have hope that we might be able to identify the parameters, but that doesn't follow either. But these are things we can kind of compute and get a handle on that help us towards thinking about this problem that we can't think about quite often for genuine complex problems. Okay. So in terms of why calibrate then, I think people have various different motivations. The simplest and most common, I guess, is you're trying to fit a model to data for purposes of model building or for explanation. You're just interested in a particular type of phenomenon. You want to fit your model to some data to see if the model can output anything that looks like real data. Okay. And if it doesn't, then we might give us hints about what we need to do to fix the model in some way. And in some ways it's simplest. We don't need to think too hard about some of the later things we're going to talk about observation errors and so on. The hardest aspect in some way is where we care genuinely about the inference problem. Okay. Maybe our X has a label, a name in our model. Maybe we call it gravity, or we call it viscosity, or whatever. And we're thinking that if we estimate X, we are hoping to learn a true physical value of that parameter. Because that's what the scientists want to do. They want to learn gravity from a bunch of simulations. So that turns out to be very challenging in most cases, unless you have kind of perfect models. The other case, which I've already talked about, is this calibrated prediction, where you want to take your inference, your calibration posterior, or your learning about X star, and push it back through the model, push forward if you like, to predict some future alternative case. And although this problem depends upon this quantity, in practice it's often a lot easier, for reasons we'll discuss in a minute, than this inference problem, which doesn't make a lot of sense, but we'll talk about why that might be in a minute. Okay? This is often easier than this, even though it depends on it. And finally, the kind of decision aspect kind of things, you want to maximize some sort of utility of some action, which we talked about. Okay. So I think the trickiest bit, and the thing we're not very good at thinking about quite often, is thinking about what an appropriate observation model is. So that is, how does our best simulated prediction, we don't know X star of course yet, but if we did, how do we think our best simulated prediction would relate to the data we have? Okay. And if we can write down something like this, it means we can score X star in some way. It gives us a way to evaluate different values of X, but we need some way of doing this. So Joanna talked about scoring all approaches more now. I'm going to kind of focus on a likelihood-based approach. but you could substitute one for the other in some cases. So the simplest case here is where you've got what I call a well-specified simulator, an accurate simulator. You know, the simulator is possible, it's capable of reproducing reality in some way. You've got you know, God's true equations, or however you think about it, you know the true laws of nature, you've implemented them without error, you can simulate it. There, it's fine. We've got standard theory, we know how everything works, statistics, happy, we get, you know, all the nice properties we know about from various statistical approaches. Okay. So once we have this, I've said this already, but once we have this relationship, it gives us a way of scoring X star. This likelihood, so this is if everything was IID Gaussian, say, this tells us how good X star is under this model F of explaining the data Y, and then we can adjust X star and try and find the value, say, that maximizes this of likelihood. Okay. Or we could replace this with a general score, proper scoring rule, or a not so proper scoring rule, or various other things. Yeah. And as always, for stochastic models, we're going to have to work a bit harder here. In that, for stochastic models, we have this kind of random xi floating around. These are the uniform random variables, say, that go into your stochastic model. Your likelihood then is then an integral. Okay, and so we often don't know this thing in closed form, and so we often have to work a bit harder. Okay. So, unfortunately, we rarely know, you know, the true laws of nature, and so instead we need to think about what happens when our simulator is an imperfect version of reality. What can we say in terms of calibration of computer models when our model is wrong in some way? So I'm going to let reality now be zeta of u. And I think, you know, there's this nice review paper, I'm going to tell you, that reviews what happens to, you know, Bayesian methods and classical methods under this kind of, when you have specified models. But the dominant paradigm, I guess, in the computer experience literature for a long time has been this Kennedy and Hagen 2001 paper. Okay. So last time I checked, it had over 5,000 citations. It's been used in all sorts of communities. So the idea there is that we assume now that the data are unbiased observations of reality. So y is zeta of u plus an error. And we're now going to assume that reality is our best simulator prediction plus an error term. Okay? So our delta u here is going to be what we call our model discrepancy. It's going to try and correct the model in some way. It's going to account for the fact that our model is wrong, and we're going to try and find the true, or more reliable prediction by doing this. So in Kennedy and Hagen, and typically in the community, we would model delta of u as a Gaussian process. Okay? But people use neural networks and all sorts of other methods. And the core idea is this. We've expanded our class of models, so we were just considering where we could only vary x in here. We've expanded it into a non-parametric world by adding a GP, by adding a Gaussian process. So we've usually expanded the class of models, and the hope is that once we've done this, we now have a class of models where the truth lies in this class of model, and it's going to allow us to learn X star, the best input. So fortunately, this idea doesn't work very well. Okay? Despite being used an awful lot, it's been known way before this. I've cited this paper just because it's Tony's paper again, pointing out one of the ways it doesn't work. So as a simple example, they imagine something where they suppose the true laws of nature behave like this. I should have called it zeta, shouldn't I? This is our truth here. Okay. And the scientists are pretty good. They got it to kind of first order, but they've forgotten air resistance or whatever. Okay. So they then think about what happens. Can we add a Gaussian process onto this to fix our inference to learn the true value of X star? And it turns out you can't. Okay. So what we've got here are, this is in a Bayesian setting, we've got posterior distribution. So this is our best guess of what X star is, our posterior for X star when we don't model the discrepancy. And this is the true value of X star. If we do model the discrepancy, so we follow the Kennedy-Hagen approach, we still get a wrong answer. We're slightly less confident. but we're still kind of wrong. And no matter how much data you collect, you're still going to be wrong. Yeah? You're just going to get more confident, but wrong. And the problem, of course, is there's a non-identifiability between delta and x star here. I could use any x star, and there'd be a delta that fits the model. Yeah? So it's kind of an obvious statement. It's taken a long time to kind of address that, I guess. Okay, and to be fair to the original authors, Mark Kennedy and Tony Hagen, they do say in the paper it's dangerous to interpret estimates of x star as estimates of the true physical values of those parameters. But what they don't do is say what x star is. So they're saying x star doesn't any longer correspond to a true physical thing. So if I got a model of air pollution that's wrong, of gravity that's wrong, and I fit it to my measurements, I'll get an estimate of something in a model that's called gravity. But they're saying we can't interpret this any longer as an estimate of that physical thing, gravity. They don't say what it is either, particularly in the paper. There's been a lot of attempts in the 2 decades since that kind of seminal work to try and recover some form of identifiability here. So there's a nice review paper a couple of years ago by Simon and Turo. So the first thing they do here is explicitly define what the x star is. Okay, so they give them a precise meaning to x star. So that if they think about E of xu being the difference between reality at u and f at x and u, so not just at x star, at any x, then they say x star, let that be the value of x that minimises the L2 norm of this error E. Okay, so if we think about this norm here, if we integrate how wrong f is at a given x across all u, that gives us the size of E in some sense. Okay. Then we're going to pick x star to be the thing that minimises the size of E. And interestingly, they then went back under this and analysed the Kennedy and Hagen style approach and showed that if we model, I've just got a slight clash of notation here, haven't I? If we, sorry, that should be E or delta. If we model this as a Gaussian process, what we find is that our posterior mode for x star converges to the minimizer of E, not under this original norm, but under the RKHS norm associated to this kernel K. Okay? So this K induces a space of functions. There's a norm associated with it. And if you collect infinite data, your estimator under Kennedy and Hagen converges to the minimum of this thing, which is not in general x star. And their argument is, well, this space is dependent upon our prior. Yeah, this is our prior for delta here. K is our prior selection, maybe it's got 3 parameters in. So they argue this is a poor choice because we get this prior dependence that never disappears. Okay, and various people have proposed approaches to try and fix this in various ways. Most of them are kind of frequentist style approaches. The one kind of Bayesian approach I wanted to pick out was a paper by Matt Plumley in 2017. They had this kind of ingenious idea. It's not very practical, but the idea in the paper was that our discrepancy model should be orthogonal to the gradient of f as x changes. And so the idea is that delta shouldn't correct things the model is capable of correcting. Okay? If f can fix it by changing x, then you shouldn't be doing the job. Okay? So the idea is if we can have this kind of discrepancy model, then in that case we recover, in some cases, identifiability, okay, of x star defined in a particular manner. Okay. Unfortunately, of course, this is very difficult to implement. For a complex model, we don't typically know the gradient and so on, but it's a really clean, nice idea. Okay, so some of the observation bit then is just to repeat this quote by Kennedy and Hagen, that we shouldn't think of x star anymore as true physical values necessarily when we have an imperfect model. I mean, and to repeat again, that prediction is easier. So the same authors, actually, Turo and Woe, who showed that calibration is difficult, if not impossible, with GP, do show that it's possible to correct your prediction. So you can do calibrated prediction, but you can't do calibration necessarily. And also, this slide's horrible notation, but just to kind of draw the link, the kind of a modern way of thinking around these things. We're getting into physics-informed machine learning here. So the idea here is if you know your equation, your simulator F solves some set of equations, then there's a class of methods that fit models that kind of minimize the misfit to your model equations and then minimize the misfit to your data. So that's kind of the idea behind physics-informed machine learning. It dates back at least to Ramsey et al. 2007, if not before, who did it with splines, but now it's very popular with physics-informed neural networks and so on. Okay. And there's the symbolic learning of equations, which is the same kind of, similar kind of idea, where we're learning a misfit to equations plus a misfit to data. Okay, we can use it as an idea to try and learn missing physics, which I think is a nicer way of doing it rather than model output. But, okay. I think the challenge for calibration for all these things is that, again, you lose any meaning in X. You can do calibrated prediction, but they're not going to fix your calibrated inference problem. You're not going to be able to learn a true physical value of the parameter very well. And of course, just a nod to talk this morning, often we don't explicitly state an observation model. Okay. Often we pick a score and minimize a score. Okay. Or we pick a criteria and we try and minimize some kind of criterion for these things. So all my early work was on something called approximate Bayesian computation, ABC, which has this kind of flavor, where a way of approximating for the prior was following some sort of algorithm where you basically measure how good a simulation is as to how close it gets to the data. Okay. And although we don't explicitly have an observation model, it turns out you can interpret criteria like that as an observation model if you wanted to. So we don't need to pick an observation model, but often if you don't, we can reinterpret it sometimes in a way that suggests an underlying observation model, which we can think about whether it's sensible or not. Okay. So we've done quantitative interest, observation models, and I'll talk briefly about the calibration framework. It'll already be obvious which kind of approach I favour here. And then I'll talk about computation towards the end. So as Vladimir said this morning, the dominant paradigm is kind of a Bayesian one. So where we start by giving a prior distribution for our known, and we try and compute a posterior distribution, how we update our beliefs about X star once we've observed the data. Okay. And this gets more challenging when we get into a likelihood-free setting or a stochastic simulator kind of setting. So I already mentioned this. If our simulator F is stochastic, we often don't know a likelihood here, which creates all kinds of problems. So I started out, I guess, as a dogmatic Bayesian, and I've become lapsed in time. But overall, I still feel it, well, I still, to misquote Churchill, I guess it's the worst form of inference apart from all the others. It's kind of my current understanding or feeling about these things. The problems with it are we get things like lingering prior dependence, and we get no nice properties for free. Yeah? We don't get calibration, we don't get frequentist coverage, we don't get robustness properties, at least not in a kind of straightforward, Lilly type application of Bayesian thinking. We have to step outside the framework to recover any of these things. So just to point then at other work, I really like the work, I don't know if it was started by Jeremiah, I don't know if he's here, but there's, one of my favourite papers the last few years is this paper by Jeremiah Knoblau and co-authors from 2019. And they start off by pointing out that the Bayesian inference problem can be recast as a variational problem, as an optimization problem. So this says that if we minimize this quantity over the space of all possible probability distributions, and if we minimize, and if we let this loss function be the log likelihood I was using before, this thing, and we let this be the KL divergence, this gives us the Bayesian posterior. Okay? So it's not a very practical way of thinking, but it's a kind of a useful way in terms of framing how we think about problem. The nice thing about it then is that they then can start to think about, well, what happens if we don't call that libel or divergence here? Okay. What happens if we don't use log likelihood, if we use a robust score, one of the things Gianno talked about this morning? And the hope is, by generalizing Bayesian inference in this way, we can get some of these robustness properties. We can get some other kind of nice statistical properties that the default Bayesian approach often lacks. So the reason Bayes and maximum likelihood often lack these nice properties is that the likelihood can be very sensitive to misspecification. Right? Small errors can throw out your entire inference when you're using likelihood here. So using something else, a more robust score, can often help. Unfortunately, I was hoping Jeremiah was here. I'm not sure this is a practical tool necessarily yet, but as a way of thinking and as a direction for the community, I think it's really exciting. And there's these post-Bayes seminars that you can join each week where the community is talking about these methods. In the kind of mainstream statistical literature, UQ literature, an approach you may not be familiar with, it's called history matching by Michael Goldstein and co-authors, Peter Craig, Ian Vernon, and various others over the last 2.5 decades, is a method designed with misspecified models in mind. So rather than having a probabilistic answer at the end, they compute something that's confusingly called a not ruled out yet, or NROI space. And this is those values of X that they can't definitely say are bad. Okay, so that's a bit confusing. What they're going to try and do is for each possible value of X, they say, is this definitely a bad X? Okay? And they judge whether it's definitely bad by picking a score, okay, and the details don't absolutely matter here, but a score that evaluates the data they do have against the model prediction at that X. And I think the reason it is attractive is this, it's very conservative. This kind of thresholding here is a justification for this 3. This thresholding creates these kind of very conservative methods where we don't need to specify too much about our model. We don't need to explicitly have statistical observation model in places. Algorithmically, it's essentially very similar, if not the same, as ABC methods, which came after. Okay? ABC has the same kind of thing. ABC is a more probabilistic approach, but it has the same kind of thing, at least in its original form, where we're thresholding some score. Okay, so I know if you're not familiar with ABC, this won't make sense, but you've got the same kind of idea here in approximate Bayesian computation, these likelihood-free methods, that we have some score that compares our simulation to the observation. Okay, and if it's close, we say X is good enough. Okay, and it gives us a kind of approximate posterior. Okay, and again, anecdotally, there's kind of reports in the literature that both these methods seem to work well in misspecified situations, and that they don't give obviously wrong answers. Okay, in a way that's not very precise. Okay, but people like David Fraser are working on making it precise. Okay. So why might these approaches work better? What do we like about them? What are the attractive aspects? Well, first, they only use some aspects of the simulator output. They kind of pick and choose what they use. So it's a bit like this kind of gives posteriors. And we move away from a likelihood function. Move away from just a general kind of comparison, which gives us strength, helps us mitigate the effective model error. I still think there's quite a bit of work to be done with kind of comparing these kind of methods with the more theoretical statistical work that's come out with generalized loss score and score minimization and so on. Okay. My personal view as well is that this thresholding is often also what makes them conservative and slightly more robust to model error in some way. There's a nice Phil David paper where he talks about what scores have robustness properties. And it's to do with the influence function, and this kind of score used here has that kind of robustness properties that people have studied in the scoring rule literature. Okay, so there's something in that, I think. Okay. So final topic then, last 10 minutes, I'll conclude, is about computation. We've picked our framework. I'm just going to talk about Bayesian methods. We've picked the observation model. How do we proceed then? Okay. And there's a nice review paper by Carl Cranmer and co-authors for 2020 that covers a lot of exciting new directions. It's obviously 5 years out of date now, which is an eternity in machine learning. But at the time, lots of exciting new directions. And the choice of method is obviously going to depend on our simulator in some way. So first of all, it's going to depend on our computational budget and the cost of our simulator. All inference has to be done with a fixed set of inference, at most n evaluations of your function, your simulator. For cheap models, n might be huge. It might not be a practical constraint. You might be able to run your model billions of times without blinking. Okay? But for complex models, like the one I said at the start, we're probably limited to a few hundred or a few thousand runs at most. So we've got to base all our computation on a few thousand simulations. The choice of method will also depend upon what we know about the simulator. Do we have to just be satisfied with first order methods or zeroth order methods, or do we know the gradient of the simulator with respect to x? Do we know the Hessian? Okay. If we know extra information, we can incorporate those kind of things into our method. Then, is it a black box kind of method? Can we get into the mechanics of what's happening? Do we know the model equations? Are the model equations easily accessible to us? If so, there's a world of methods out there that might be feasible around multi-fidelity and so on. But often, when it's a big, complex model F, the equations are too complex to want to get into. To modify the computer code itself is just too big a challenge and unattractive as an approach. And finally, how quickly do we need the answer? It's fine if we can think about the answer for a day or a week to compute the posterior. If we need the answer in 10 minutes, like at the start, what are we going to do? So I'm going to distinguish briefly between case-based and amortized inference. So the idea behind case-based inference is this is what everyone will be familiar with. And the idea here behind is for each data set we have Y, we run a separate algorithm of some sort to learn the posterior. Someone comes along with a new data set, we have to run the algorithm again. MCMC or whatever it is, we have to start over, redo the calibration. An emerging trend in machine learning, it's very exciting, again, is these amortized inference methods. So that there you hope to do a large amount of upfront training to give you a way of estimating the posterior for any feasible dataset Y. So that when the new dataset Y comes in, the reporting of your posterior is cheap. It's essentially immediate. You've done all that upfront work to approximate all possible posteriors so that when the data comes in, whether that's feasible, that's kind of the hope of that field. Okay. So in terms of case-based methods, I don't want to talk about them particularly. The gold standard remains methods like MCMC, Markov Chain Monte Carlo. We don't need to get into the details, but what you're going to do there is sequentially simulate values from the posterior distribution. And you do that by proposing, suggesting a proposal distribution, how you're going to move around in X space, in parameter space. And then with each proposed move, you either accept it or you reject it. And there's 40 years worth of literature on doing this efficiently. If you know the gradients of F, then you can use fancy methods like Hamiltonian Monte Carlo, or if you know the Hessian, you can use Riemannian versions and lots of clever ways to speed this up. But unfortunately, at least for the models I work with, for most complex models, MCMC is still going to be computationally infeasible. Okay? You're going to need to simulate probably hundreds of thousands of simulations, and each simulation involves an evaluation here that depends in some way on the simulator. So unless your simulator is relatively cheap, a few seconds at most, you're not going to be able to do these kind of methods very easily. So a cruder form of approximation, I think there's some really interesting work by Andrew Stewart and collaborators on looking at these ensemble Kalman methods. So whenever you see the word Kelvin, it essentially means you're assuming something's approximately Gaussian underneath. So what they try to do there is the same kind of idea. You're going to have a small set of particles, and you're going to approximate the posterior with the particles, but you're kind of assuming it's approximately Gaussian underneath. Okay. So again, the details don't matter here. It started off with this paper by Evanson, which generalized the Kalman filter, which is exact for linear systems, to nonlinear systems. What the recent work has been doing is applying this work by Evanson, which was a filtering setting, so i.e. where you get time, observations coming in time, to a static setting of the kind I've been talking about, where there's just one data set, there's no time in the problem necessarily. And so there's a number of papers analysing these kind of methods that work by modifying a set of particles through time, kind of methods like this. Their argument is that this is this approximate a gradient descent kind of step. And you can, by modifying your data, so this isn't the real data, it's a modified version of data, you get something that converges relatively fast towards something that approximates the posterior. Okay, so if you're not familiar with that kind of work, I think that's really interesting. And the nice thing is it works with far fewer simulations than MCMC, for example, because you're assuming everything's Gaussian underneath, essentially. Okay, another kind of approach that again hints back to the kind of thing I talked about before, the generalized Bayes, is a variational inference style approach, where instead of trying to sample in some way from the posterior, we instead aim for an optimization-based approach. So a simple approach would be to assume the posterior takes a particular parametric form, and then you try and then make that approximation to the posterior as close as possible to the true unknown posterior. And if you write this in the right way, certain bits of this calculation drop out, and we get something that's computable in some cases. So it gives us a way of trying to approximate posteriors. Again, for it to work well, we typically need the derivatives of the simulator, which we probably don't have in many cases. So again, the core of the statistical community is based around this idea of a surrogate method. Okay, so because we are faced with working with just a finite ensemble of simulations, an obvious kind of idea, it's used a lot, is can we approximate our simulator F by something? So one assumption we might make is that we're going to model F as a Gaussian process, train it given this ensemble of simulations that we could afford to do, and then we can do inference based on our surrogate model or our emulator. Okay. And so we can make a lot of these methods practical by doing them then with an emulator or a surrogate. Okay. So just think of GP as a kernel regression, for example. Okay, I'm going to skip that for time. So just finally, say briefly something about amortized inference. The aim, as I said, is to train a model that gives us a fast estimate of the posterior for any y. So I think the most popular approach at the moment is based around using these normalizing flows. And the idea is, we already saw this morning in Joanna's talk again, this kind of inverse transform kind of idea, that we're going to try and find a G that maps samples from the posterior to a Gaussian. So it normalizes the data in some way. So I think you had it transformed to a uniform, didn't you? But the same kind of idea. Can we always, and in theory, we can always find such a G. And so the idea behind this community is you let G be a big invertible neural network. You do a ton of simulation. From you pick x's, you simulate y's, you pick x's, you simulate y. Can we then learn this invertible transform that makes this G? Okay? And if we can find an invertible G, then at test time, when we get a new piece of data, we can generate samples automatically from the posterior. So on paper, it's this very simple, attractive idea, I think, that if we could make something like this work, it would save us a lot of time if we could amortize the cost of our inference. Just upfront training would then make, like our cardiac example, a feasible tool or approach. It's not clear how well this is going to work in genuinely complex problems, I think, at the moment, but it certainly works very well in some simpler problems. It's just published. Okay, so just to finally then touch back before we finish, what can we do in this kind of place where we started? Remember, we've got this propagating wave. What kind of approximations do we have to make any kind of progress here? So we've done various different methods here. The first thing we try and do is build an emulator. Okay. So a Gaussian process that approximates the simulator using a selection of simulations from the model. And we have some difficulty in how we do inference on a complex shape. So Slava in the first workshop talked about these kind of methods, GPs on manifolds. And so we've been using those kind of ideas in here to create surrogates that know something about the geometry of the shape we live on. And then Maria, who's at the back here, has been talking about, I've been looking at using ensemble common filter methods to do fast inference. So with this surrogate, can we then get an estimate of the parameters that is good enough to say something useful in the clinic? Okay. So what she's got working is something that can, with as few as kind of 50 training simulations, which we can do in advance, we could get an estimate of the posterior in almost real time. It takes a few seconds once we've done that upfront training. Unfortunately, there's non-identifiabilities everywhere, and we made very strong assumptions, but it's kind of the limit of what we think is possible at the moment is as a way of getting very fast estimates of some of the parameters in the clinic. Okay? And this gives us some improvement in the AF prediction from our prior, not as much as we'd like, and so we're looking at what extra information could we incorporate to improve our prediction of atrial fibrillation. Okay, I think I skipped that. So just to conclude then, I think this is my personal reflection again, when we're working with real scientists, with kind of real models, I mean, not real scientists, we have, we often have to compromise in some way on the kind of things we would like to do as careful statisticians, and it's thinking about what compromises are reasonable and going to be acceptable and which ones are dangerous to us. And we're slowly thinking about that, but theory lags as always behind practice by some distance, and there's people here thinking about the kind of the theory to understand how the danger of certain approaches or the safety in certain approaches. And so I think there are lots of issues in calibration that relate to the challenge of this program here, how we can use more robust scores, how we can get some concept of calibration as the sense mentioned this morning in calibration here. How can we do multi methods work in practical examples and so on? Anyway, I feel like I've been talking for hours, so I'm going to finish there. Thank you for listening.
Thank you very much. Do you have questions? Yes.
Thank you very much for the nice talk. In the beginning, you talked about certain statistics called Sobel indices. Can you tell us more about what they actually mean or how they are used for this identifiability?
So they're not used for identifiability as such. People. We talked about this last week with Simon. The community can't assess identifiability. There are symbolic ways of doing it, but they typically only work, in my understanding, for small sets of ODEs. They don't work for big complex models. Sensitivity indices are things we can compute. We don't need any gradients to compute them. We don't need to have any knowledge of information matrices or anything like that. They are just ways of averaging the importance of each parameter across the input domain. So you have a kind of a prior measure across what the feasible parameters is, and you average how much the function varies with respect to that measure, that distribution, and it gives us some numbers that we can trick ourselves into thinking relate to how easy it's going to be to estimate those parameters. It's basically, I think, how the community uses these most often.
I think we have Peter in the back. Was next.
So, I question the idea of X star, whether there exists an X star which is the best set of inputs. Given we have a vector of outputs, the best for Y1 is not necessarily the best for Y10.
Yeah.
And something that gets temperature, a climate model that gets temperature in Cambridge right, but drives the Gulf Stream backwards, would not be a good climate model.
Yeah. I agree. I mean, we have it here essentially. We collect one set of data under a very precise clinical protocol where we simulate this first kind of well-behaved wave, and then we hope to predict what the model's going to do under another set of circumstances. And it's not clear the same set of parameters is relevant to either. You know, it's the same set. But I don't. Do you have suggestions for what we should do?
Well, that's why I like history actually, because it doesn't try to give you the best.
Yes.
It gives you a set of good.
Yeah.
Well, I said not bad. I'll check my right. What Michael Goldstein would call not totally stupid.
Yes.
And I think not totally stupid may be what we have to aim for, rather than trying to optimise it.
Yeah, no, I have a lot of sympathy, as you know, for these kind of methods, which, as far as I know, there's been very little kind of, the kind of study that in Italian people do, where we look at convergence and consistency of the estimates and so on. It'd be really interesting if we could interest some people in understanding these methods while we're here, I think. Yeah.
Maybe just a comment to what was just the question, but I thought that your optimum is always with respect to the quantity of interest. I mean, you said that you do it for a particular quantity of interest. Your example of climate model versus temperature over Cambridge would be two different quantities of interest. So it's a different Y star, X star in his scenario. Did I understand it right? I thought your X star is in some sense dependent on the quantity of interest.
That is how mathematicians analyse it when they come to study what the methods are doing. I don't think it's how the user community thinks at all, and it's not how the standard Bayesian kind of community thinks either. Often what X star is remains undefined. It's the thing that we have a posterior distribution over. But yes, the kind of more careful analysis starts by clearly defining X star into the quantity of interest. And I think that is a good approach, and would partly answer Peter's question.
So my question was related to this thing that you highlighted now, that the non-identifiability, like say this X times U example. And then you had this example by Plumley, and as you know, I like when there's a challenge in computation. So
yeah.
Where is the challenge? So because I also think this should be the way forward to orthogonalize in some sense.
Yeah, I think the challenge is.
And you didn't mention in some sense instrumental variables. So what if you have a second type of observation on the same U, so that you could kind of use that in order to find an orthogonal.
Yeah, I think there are situations where if you have the right kind of measurements, you can make the Kennedy-Hagen kind of approach work. Okay, not often the kind of measurements we have, but the challenging nature here is that we typically don't have the gradient of the simulator.
But
we could approximate it.
In many examples, you have adjoints.
Yeah, absolutely. So we've been looking at adjoint methods in work I didn't mention here with Chris. Not particularly in this setting, but again, my knowledge of adjoint is fairly limited. We're kind of in the world where we can write down an adjoint for a linear PDE, but as soon as someone gives me a big set of 50 equations that are in their climate model, I have no idea where to start with that.
Unfortunately, the math office is sort of kicking it out because I like 4D1, so I mean.
Yeah. Yeah.
I think there was a question. Do you have a question?
Yeah, how do we think about identifiability in the stochastic setting? If we have a simulator that depends on the stochastic output and doesn't give you deterministic mapping.
So I guess the way people would think about it would be the parameter is identifiable there if the distributions are different whenever you have two different parameter values.
Is it about strict equality of distributions then?
Yes, exactly. Yeah. Whether we can assess that for stochastic simulators, but yeah, I think that'll be the definition.
Good. And the last question?
Thank you for the nice talk and review of all methods to approximate posterior in this way. Just, I need to ask one, two. You also advertised one method, invertible neural networks. In which conditions we can find this invertible function? I think we need some sufficient conditions for the existence of that kind of function, which is the inverse of that posterior. In which circumstances we can find this invertible neural network? Or
I don't know. You'd have to go to the papers. Certainly, in a very general class of models, you can. I'm hesitating to say all. Maybe if the simulator is continuous, I think there definitely exists. Whether we can find it is a different matter. But I think in a very wide enough class of models, I think such a G will exist.
yeah.
Several people are nodding in the audience, so hopefully I've not made something up there, but that's my understanding.
This is nice.
Good. Let's thank Richard again.